Alright, this is going to be our third video in our current, resistance, and electromotive force module. Everything I'm talking about in this video maps to section 25.4 from the text. And there is one subsection at the end of 25.4 that I won't be talking about in this video. They discuss it after all the examples that they do in this section, and so I'm just going to move that subsection to the next video. But for now, we can get into the discussions that they have in section 25.4. We're going to talk about electromotive force or EMF and circuits. But before we do that, we need to talk about conductors and why it is that we can't have a steady current in an isolated conductor. Okay, so for us to have a steady current in a conductor, it has to be part of a closed loop or what we call a complete circuit. And this is because if we have a steady current in an isolated conductor, what's going to end up happening is we're going to move a bunch of charge from one side to the other of the conductor. All this charge is going to pile up, and it's going to set up its own electric field, which is going to counteract the electric field that we've put into this conductor to create this initial current, right? And so that's what this figure below here is sort of showing. We can imagine initially we have some sort of isolated conductor here. We apply this electric field to set up our current. Our current is set up, and charge starts to flow from the left to the right here. Our positive charge starts to flow left to right. And so what do we end up having? We end up having a buildup of negative charge on the left-hand side and a buildup of positive charge on the right-hand side, slowly building up as we apply this electric field. I say slowly, but really this would all happen almost instantaneously as we apply an electric field to this thing. So we have this buildup of charge, and as we have this buildup of charge, the charge itself starts to set up its own electric field, right? There's going to be an electric field pointing from our positive charge to our negative charge. That's E2 here, where E1 is the electric field that we originally set up to produce our current. So this E2 starts getting set up by these charges, and it starts to counteract our E1, and our current is slightly lower now. And quite quickly we get to a situation where there's too much charge built up on either side of our conductor. We have too much negative charge on the left, too much positive charge on the right. The magnitude of E2 becomes equal to the magnitude of E1, and we no longer have current flowing, right? We just have charge built up on either side, and we can no longer sustain a current. And this would happen, as I said, almost instantaneously. This would set up very, very quickly. Okay. So for a conductor to maintain steady current, it needs to be part of a complete circuit. Okay, so we need this conductor to be in a complete circuit, and this complete circuit. So we're going to have maybe I'll draw something here. We can imagine a complete circuit like this. Okay, so let's imagine we had some sort of a complete circuit, very, very simple, and we have our current flowing. Let's say it's flowing in this direction, right? So the current's going to start flowing around our loop here, but for the current to be flowing, there needs to be some change in potential energy, right? The current is only going to flow from high potential to low potential. So for this thing to be able to flow, we need something placed in this current loop that's going to increase potential energy, right? And this is very much, you can imagine this like a water fountain. So if you look at a water fountain sprays water out the top of the fountain. It falls down into the pool below the water fountain, right? So it starts off at the very top of the water fountain with high gravitational potential energy, and then the water falls and it lands in the pool below where it has its minimum gravitational potential energy. You then need a pump to suck the water from the bottom of the sort of pool or tank or whatever, and move it back up to the top of the water fountain to spray it out again. If there is no pump to supply to move this water from low potential gravitational energy to high gravitational potential energy, the fountain doesn't work. All the water just sits in the pool at the bottom, and that's it. The situation is very similar for an electric circuit. We have all this charge flowing. It needs to flow from high potential to low potential. We need something in this circuit to move the charge from low potential to high potential so it can go back around the loop. Okay, and we're going to see, maybe I won't include this drawing here since there's not much detail to it. We're going to see what it is that gives us that sort of bump up in potential that we need to be able to keep the current flowing around the loop. Okay. So now electromotive force specifically, which we generally are going to abbreviate as EMF, the influence that makes the current flow from low potential, from low to high potential, I should say, is called EMF. Okay, EMF for short. And EMF is an energy per unit charge. So it comes with SI units of volts, just like our potential difference does. And a typical EMF in a circuit might be something like a battery, right? So if we go back to my drawing, and actually we're going to kind of see it more here, so maybe I won't redraw it, but a battery would be a good source of EMF in a circuit, right? We have a circuit connected, charges flow through the wire from the positive terminal, positive charges flow from the positive terminal around the loop to the negative terminal, but then the battery takes those charges at the negative terminal, raises them up to a high potential, and in the case of a battery, what's doing this is some chemical reactions, and then once the charge is back up at high potential, it goes back through the loop, right? So we're going to take a look at this a little bit more carefully here in a second. Here I talk about an example where we have a flashlight battery that might have an EMF of 1.5 volts, which means that it does 1.5 joules of work on each coulomb of charge that passes through the battery. Okay, and we're going to use this symbol, this curly E, to be our symbol for EMF. Okay, so that curly E from now on is going to mean EMF. In ideal sources, so for an ideal battery, the EMF is going to maintain a constant potential difference between its two terminals. Okay, and this is going to be independent of the amount of current that we have flowing through the battery or through our circuit. Okay, these perfect sources of EMF don't really exist in the real world. Okay, they're like massless ropes or frictionless surfaces. They can be decent approximations. They're good models to work with to understand the systems, but in reality, there's no such thing as a perfect source. Okay, but to start off with, we are going to look at one of these perfect sources, and then we're gonna quickly transition to an imperfect, more physical source. So the diagram below here shows an ideal source of EMF, and so, well, let's take a look at it here. We have our let's assume this is a battery here. We have our positive terminal here. We have our negative terminal over here. We're going to have some potential difference set up between points A and B. A is our positive terminal, B is our negative terminal. And so there's going to be an electric field set up inside of the battery, right? We're going to have an electric field pointing from positive charge to negative charge. And so these positive charges are going to feel a force, an electric force in the direction of the electric field equal to QE, right? So this is our electric force here, okay? But the battery, or I guess whatever our source is, in this case maybe a battery, is going to provide a force Fn, which is a non-electrostatic force, which is going to tend to move charge to higher potential. So it's going to take charge from low potential coming in here at B, and it's going to move it to high potential up here at A. So Fn is going to work against Fe, right? And it's going to be moving charge from low potential to high potential. Okay, so that's what we see drawn out here in this diagram. Okay, so well, maybe the best thing to do is just to move on to the next sort of discussion here. So if a charge of plus Q is moved from B to A, right? So if we're moving this charge from B, our low potential, to A, the high potential, okay, Fn is going to do work equal to Wn equals Q times our EMF, okay? So it's going to do this work on that charge. This displacement, the displacement that the charge is undergoing, right, is opposite to the force Fe, the electric force inside our source, right? And so the potential energy associated with this change is increased by Q of VAB, right? So we're moving this charge from low potential to high potential. Is a potential energy change, and that change in potential energy is going to be equal to Q VAB. Okay. For an ideal source, and again, these ideal sources are sort of mythical; they don't actually exist. For an ideal source, we're going to have Fe equal to Fn. Okay, so if these things are equal, well, equal in magnitude but pointing in opposite directions, in that case, the total work done on Q is 0. There's an increase in potential energy, but no kinetic energy is changed, and so we have this expression that we see here, right? We see Q times our EMF is equal to Q times our potential difference between VAB, and that means that our EMF is equal to VAB. But remember, this expression here is only true for ideal sources. Okay. If we took this ideal source and then connected it to some wire, let's say to the circuit that we have below here, we can sort of see what's going to happen. So we can imagine that this wire has some resistance R, let's say, for example, and so now we've hooked up our battery or whatever our source is, and we can see how the charge is going to flow. Right, we're going to have charge flowing, so we're going to have current moving this direction. We're going to have some current I. The current's going to flow this way. It's going to flow from high potential to low potential, and as our charge reaches low potential here, depending on what the source is, but in the case of our battery, the chemical processes in here are going to exert some force Fn against our force Fe. We're going to move the charge from low potential to high potential, and then this charge is ready to go back around the loop, right? And it just keeps going in this sort of loop, right? So we have no charge building up anywhere. We just have our source of EMF here, which is giving us a way to sort of lift things from low potential to high potential, so it can sort of slide back around, back down to low potential again, and just go around the loop again. Okay, so that's the sort of setup we want to have in mind when we're working with these kind of setups. So we know that VAB has to be equal to IR, right? We know Ohm's law here, and so this means that our EMF, which is equal to VAB, has to be equal to IR for these cases of ideal sources. Okay, but that's about all we're going to do with ideal sources. We just wanted to get the idea of it, and now we're going to talk about the internal resistance associated with these sources. So batteries or generators or whatever you want to think about. And all sources are going to have these internal resistances. These internal resistances are going to make it such that our VAB cannot be equal to our EMF. Okay, so whenever you have a real source, you're never going to have an EMF equal to the terminal potential difference, the VAB. Okay, and so that's what we're saying here. Basically, the expression that we end up with is simply that our VAB, our terminal voltage, is going to end up being equal to the EMF of the source minus the current going through the source times the internal resistance. Our small r here is this little internal resistance associated with the battery or whatever, right? So there's some small resistance for current going through this battery, and it's going to make it so that our VAB cannot be equal to our EMF. Okay. And so the terminal voltage VAB, that's not right, this is a typo. So the terminal voltage of VAB has to be less than our EMF always, okay? Because these are all positive numbers, right? So our EMF is going to be some larger number. We take away some positive number from it, our VAB will have to be smaller, okay? And so for a real source, the EMF can only be equal to VAB if no current is flowing through the system, right? And so only if I is 0 do we end up with VAB equal to our EMF, okay? And so we can write this expression that we have here. We know that VAB has to be equal to IR, and VAB is also equal to the expression that we have up here, which is our EMF minus our current times our internal resistance. And so if we rearrange terms, we end up with a very useful expression for the current. Our current is going to be equal to our EMF over the external resistance, like the resistance of the actual circuit, and then the internal resistance associated with our source. Okay? So we're going to want to keep this one in mind, so I've boxed it, and we can move on here. So this next section, the textbook discusses a number of symbols. We're going to use these symbols quite a bit over the next at least 2 chapters, and so we should probably be sort of aware of what they mean here. So this straight line here, this is just going to be a conductor with negligible resistance. Okay, so we just have a just a wire with very, very low resistance, something that we're just going to completely ignore for our calculation. When we have this jagged squiggly line, this is a resistor, so this is going to come with some value, or we're going to want to solve for the value. It'll usually be in ohms or whatever, right? So we can sort of solve for that. We're going to have a source of EMF, so our sources of EMF look like this, with the positive terminal being on the large thin bar side, and on the smaller thicker bar side, that's going to be our negative terminal. It's going to have some EMF associated with it. Okay. Now, for real situations, our EMF is always going to have to come along with some internal resistance. Okay, and so we can see it here. This sort of beige rectangular area is meant to indicate some sort of a source, could be a generator or battery or whatever, and it's going to have some EMF associated with it and some internal resistance. Okay, so we have 2 different setups here. Either the resistors on the positive or negative side. That's not going to make a big difference for us. The last 2 symbols here are 2 different types of meters that we can attach. This is a voltmeter and an ammeter. Our voltmeter measures a potential difference between the 2 terminals of the voltmeter. Idealized voltmeters have infinite resistance, and so we're always going to think about idealized voltmeters when we hook things up, and we're going to think about it having infinite resistance, and so it's just measuring the potential difference between its 2 terminals. Ammeters are going to have 0 resistance, and allow current to flow through them freely, and so we want to think about sort of idealized ammeters when we're using them to measure current. Okay, so those are our symbols that we're going to use, and now we're going to take a look at a few examples. Okay, and I have some numbers worked out over here that we can look at. So we're going to start off with 25.4 here. In 25.4 we have figure 25.16, which shows a battery with an EMF of 12 volts and an internal resistance of 2 ohms. And so 2 ohms is a pretty large internal resistance, but we'll just go with it for this example. The wire is to the left of A, so the wire over here, and the wire over here to the right of A, or of our ammeter, are not connected to anything. So we want to determine the respective readings of VAB from our voltmeter and I on our idealized ammeter, right? So what are these going to end up being? Okay, I'm going to leave the drawing on here, and then I can maybe write down here. Maybe I made these a little too large, but we'll go with it anyway. So V is an idealized voltmeter, right? And so no current can be flowing through our idealized voltmeter. It has an infinite resistance, and so I has to be 0 through the voltmeter. And so since there's no current flowing through the voltmeter, and this chunk of circuit here is not connected to anything else, there can be no current flowing at all, right? There's nowhere for current to flow. We spoke about how current can't flow through an isolated conductor, right? And so what does that mean? Well, that means that our A is going to read that our current is equal to 0, right? There can be no current flowing through A. But since I is equal to 0, right? Since I is equal to 0, that means that if we think about our expression, if we think about VAB equals E, and my E's when I write them like this look a lot like epsilons. Maybe I'll try to write them like this. Is equal to IR, right? But we just talked about how I has to be 0, right? There can be no current flowing. And so this means that VAB, the reading of our voltmeter, is actually going to be just equal to our EMF. And what does that mean? Well, that means that our voltmeter is going to read VAB equals 12 volts. Okay, that should be an equals. Okay, so that was a sort of simple conceptual first look at what some of these problems might be like. Let's take a look at a only slightly more complicated one. So in this example, we add a 4 ohm resistor to our battery from the example we just looked at, right? So our 4 ohm resistor is now going to be connected in the loop here. Okay, and we want to know what the voltmeter and ammeter are now reading after we make this this connection, right? So we can kind of go through the calculation a little bit. I'll leave that there. So first we're going to want to find what our ammeter is reading. What is the current flowing through the ammeter? Okay. So we know that I is going to have to be equal to, and I keep doing it, but that, like that. Okay. So we know from our equation that we have boxed just up here, equation 1, that our current has to be equal to our EMF over our external resistance plus our internal resistance. Well, we have all these values. We can just write them down. We have 12 volts for our EMF. We have an external resistance of 4 ohms. We just added that in, and we're given an internal resistance of 2 ohms. And so we end up with a current of 2 amps. Okay, so this is what the ammeter reads. Okay, and then we want to see what our voltmeter reads. Maybe I should have our voltmeter visible to us here. So the voltmeter is going to read what VAB is, right? Except that VAB is going to be the same as VA prime VA prime B prime, right? Why is that? Because our ammeter has no lets current flow through it freely, and so has no potential difference across it, and so the potential at B has to be equal to the potential at B prime, and the potential at A has to be equal to the potential at A prime. And so what does this mean? Well, this means that VAB has to be equal to VA prime B prime. Okay, but let's look at sort of across from A to B and from A prime to B prime, right? Across A to B, well, we know that VAB across A to B from the expression that we just generated earlier has to be equal to our why do I keep writing it like this? There we go. To our EMF minus our current flowing times the internal resistance. And we know that across A prime, B prime, across this resistor, well, V equals IR is the expression that we know for that, and that's just Ohm's law, so this has to also be equal to IR, okay? And we can just substitute in numbers. We're going to see that both of these end up being the same. So if I substitute in numbers for this first expression, we're going to end up with 12 volts, that's our EMF, minus 2 amps, that's the current that we found flowing in the first part here, times our internal resistance, which is just 2 ohms, right? And if we do that calculation, we're going to find 8 volts. And would we find the same thing as we go across from A prime to B prime? Well, yes, we would. We end up finding that it's, again, 2 amps, right? That's our current flowing around the whole system. But now we're going across 4 ohms of resistance, so this is across 4 ohms. And if you do that calculation, you also find 8 volts, right? And so this is giving us the same potential difference, and this is because VA is equal to VA prime, VB is equal to VB prime, and this means that VAB is equal to VA prime B prime as we initially said. So really the answer to the question is, well, the voltmeter is going to read VAB equals 8 volts. Okay, and this sort of doing it both ways thing is just a double check to make sure that we're understanding sort of how this is all going to work. Okay, so that's that one. I have some numbers for the next ones. We have two more examples we're going to look at. We have conceptual example 25.6 from the text here. And we're going to be using, again, using voltmeters and ammeters. But now we're going to use the same circuit we had before, right? We're going to use the same circuit, but now we're moving the voltmeter and the ammeter around, okay? So let's take a look at sort of what happens here. In part A, we've simply flipped where the voltmeter and the ammeter are, right? So what do we kind of expect to see happen here? Well, really, we've done nothing, right? We've just, the current flowing around the loop is going to be the same as we had before, and now we're testing for VA prime B prime instead of VAB, but we just argued that VAB has to be equal to VA prime B prime, so we expect that it's all going to turn out the same, and that's exactly sort of what we're going to end up finding. I'm not going to go through the whole argument, but we can see from our work above that VAB is just, again, going to be 8 volts, okay, and this is what our voltmeter reads. And the ammeter has just switched from this side to this side, but the current has to be the same around the whole loop always. And so what's going to end up happening? Well, nothing. We're just going to end up with our ammeter reading 2 amps, right? That's going to be our current, okay? That's for part A. What's going to happen in part B? Well, part B, things are going to change, right? Because now our voltmeter is actually stuck in the circuit in series, right? And so now we can't have any current flowing, right? Because our voltmeter is an idealized voltmeter, it has an infinite resistance, and so because of that, so the voltmeter implies resistance is equal to infinity, right? And so we can't have any current flowing. Well, this means that I equals 0, and that means that our ammeter is going to read 0, right? So no current is flowing around this this loop, right? And so that kind of answers the what the ammeter is going to read, but what is the voltmeter going to read? Well, the voltmeter is basically trying to find what the potential difference between B and B prime is. So what the voltmeter is looking for is basically VB B prime. But there is no potential difference between B and B prime. We just talked about that in the previous example. VBB prime is just going to be equal to 0 volts. Okay, so the voltmeter is going to read 0, the ammeter is going to read 0. Basically nothing is happening on either of those meters. Okay, so that was another conceptual example, and we have one last example I wanted to look at here. And this doesn't quite finish off the section, but as I mentioned, we'll finish off the last little bit of the section in the next video. So this is going to be 25.7. We have a source with a short circuit here, and so what happens? The circuit from example 25.5. So two things ago. Maybe I'll just redraw it here instead of scrolling up. We're going to replace the 4 ohm resistor with a 0 resistance conductor. So we're just going to replace it with a wire. And we want to know what the meters are going to read in this case. So let me just redraw what we had above. We have points A and B here. Call these A and B. We had some source here. This source had some internal resistance like this. We had a voltmeter set up like this. We had our wire coming around like this. We had A prime here. We had B prime here, and before we had some resistor like this. This was a 4 ohm resistor before, but now we're gonna chop out this 4 ohm resistor. We're gonna replace it with just a wire. So we're gonna have resistance equals 0 here, and we now want to know what these meters are going to read, right? I forgot to include the ammeter here, but we basically have a idealized ammeter here. Okay. And so we want to know what these things are going to read, right? So let's take a look. The first thing we can look at is, well, what's the ammeter going to read? We have this expression. We know that our current I is going to be our EMF over our external resistance plus our internal resistance. But in this case, we have no external resistance. We've replaced the external resistor with just a conductor. So basically our R is going to go to 0, and we're just going to end up with this expression here. Well, we can solve for that. We were told, and I forget the numbers, I think this thing was an EMF of 12 volts, and I think our internal resistance here was 2 ohms, okay? And so if we do that calculation, we're going to end up with 12 volts over 2 ohms, and we end up with 6 amps, okay, with 6 amps flowing through the system, right? So that's what the amp meter is going to pick up. What is the voltmeter going to pick up? Well, we can kind of look at this simply by using the expression that we have above. We know that VAB has to be equal to our EMF minus I times the internal resistance, right? And so we have an EMF of 12 volts. We have a current of 6 amps, and we have an internal resistance of 2 ohms, right? So if you do this calculation, you're going to find that you end up with 0, right? And this is exactly what we would expect, right? Because we have no resistance on the outside, so it's kind of like a short circuit. We end up having a potential difference of 0. This is all sitting on the same conducting wire, and so there is no potential difference between the two of them, right? Okay, so those are the 4 examples from this section. As I mentioned, there's going to be one last little thing we're going to look at in the next video, but I'll leave it here for now, and I'll see you guys in the next one.